Okay, so we're continuing on with our protein binding discussion, our drug protein binding discussion. If we consider that the fraction bound of drug, we want to know the fraction unbound and the fraction bound. This is very important because it dictates how the drug can move through the body, whether or not the drug can actually act. And remember, if it's bound to a protein, it can't interact with a receptor, therefore it's inert. So in order to determine we want to be able to determine the fraction bound and therefore the fraction unbound of any drug at any point in time, don't we? So the fraction bound is going to be our bound concentration over the free concentration plus the bound concentration of our drug. So this is our total drug concentration, and this is our bound concentration. So bound concentration over total is going to be our fraction bound, isn't it? If we put in all of our determinants here, we'll actually come up with this equation, which is quite convoluted. I wouldn't expect you to memorize any of this, but you could come up with this algebraically. So our fraction bound can be determined by our capacity and our affinity. So N, the capacity of the system, and the affinity of the drug for that protein, or N is the capacity or the number of proteins, and Ka is the affinity, and then our free drug concentration that's available. So what happens when the number of binding sites available goes down? Well, we're going to predict that if the number of binding sites available goes down, we're going to have less binding, right? Because there's not as many sites to bind to it. So if we remember that N is the number of binding sites, and we have a decrease in the number of binding sites, we can see in this equation that if the N decreases, this whole number is going to increase, isn't it? So if the denominator increases, what happens to the fraction bound? It will also decrease. So that makes sense, right? If we have fewer binding sites available, if there's a decrease in the capacity of the system, the number of binding sites, we're going to have a decrease in our fraction bound, which would be an increase in our fraction unbound. What about if affinity changes? And obviously the inverse would be true. If we have an increase in N, we're going to have an increase in our fraction bound and a decrease in our fraction unbound. What about affinity changing? What happens when another drug with a lower Kd is introduced or a higher Ka? So we need to change our Ka to a Kd. So we have a lower Kd. In other words, there's a lower concentration needed to have half of the binding sites full. So we have a higher affinity here if we have a decrease in our Kd, a decrease in our Kd. So if we replace our Ka with 1 over Ka or Kd, we'll end up with this equation, right? You can see this is the same equation, just in terms of Kd. What happens when our Kd decreases? Well, then our denominator is going to decrease, which will increase our fraction bound, won't it? So our fraction bound will increase and our fraction unbound will increase or decrease. Therefore, if a higher affinity drug is added, we're going to see an increase in the fraction bound of that drug. And the opposite would be true. All right, I'm going to stop there. Well, maybe we'll go on. Here's our major binding proteins that we have available. Albumin is the most important binding protein because it is the most highly available. As you can see, there's about 42 grams per liter in most patients. Now, if you have somebody that has hypoalbuminemia, less albumin available, then you're going to have a decrease in your N in that case and less binding sites available. So you could have a decrease in binding in that case, right? You can see the molecular weight is 70,000. It's synthesized and eliminated in the liver, but an interesting thing is it's about a 3-week half-life, which means you're not going to see abrupt changes in the number of binding sites available, because it's going to take, what's 3 weeks times 5, 15 weeks So what is that? That's like 4 months or so for things to come to a new steady state. So this will not change abruptly, but you can say increases and decreases in the number of protein binding sites available. AAG is really an interesting one. It stands for alpha-1-acylglycoprotein. It has a smaller molecular weight, but it's still a large molecular weight, right, compared to drugs, which are about 300 usually, in the 300 to 500 molecular weight range. This has 40,000, right? So if it gets attached to an AAG protein, you're going to have a very large molecule complex, right? What's interesting about AAG is you can see very wide changes. It can increase, it's an acute phase reactant, so it can increase quickly. You can see a large increase in AAG. And isn't this a great way for the body to defend itself? So just think, if you were designing the human body and a toxin comes into the bloodstream, isn't it a great idea to throw out a bunch of proteins that will complex with that toxin and make it inert because it's now bound to the AAG? Isn't that a great protective device? That's what AAG does. So it increases during times of trouble, and it has a much shorter half-life. But it's still, almost a week, and it's synthesized and eliminated in the liver as well. The third type, which is the least important because it's not very common that drugs are bound to lipoproteins, but it's a cholesterol, right? So if a patient has high cholesterol, they're going to have more binding proteins. If they have a lower cholesterol, or if you're trying to lower their cholesterol with drugs, you can see a decrease in their N here. And again, synthesized and eliminated in the liver, and the half-life is about 6 days. All right, we're going to pick up here.